In this video, we are going to look at a very famous result about rational numbers, which is that rational numbers are what we call dense on the real number line. Here's a working definition of what density means. We say that the rational numbers are dense because between any pair of numbers, say a less than b, you can find a rational number sitting between them. So imagine we have such a pair of numbers, a and b, on the number line. This result that we are about to prove in just a moment, I lost my marker I was looking for. Okay, let's use pink. Tells us that there is some rational number between a and b. And what's kind of exciting about this result is that you can keep going with pairings now. So let me focus on r and b. Between r and b is another rational number. Let's call this one r sub 1 and this one r sub 2. And then between r1 and r2 is another rational number. And then we have another rational number, and then another rational number. And I think that's a really exciting idea, is that the more you zoom in on the number line, it doesn't matter. You're always going to be able to find rational numbers, no matter how close together the numbers are. So we are going to prove this, and I'm going to start the proof. We'll end up breaking it up into cases, but I think we can get a nice proof going in just a moment. Let me erase this, and then I will come back. The first thing we are going to do is recognize that since a is less than b, 0 is less than b minus a. So by the Archimedean principle, there exists some capital N from the natural numbers so that 1 over capital N is less than b minus a, since this is a positive number. All right, let me just do a little rearrangement here. Thus, just moving terms around, a is less than b minus 1 over n. And I could actually go a little further with this. B minus 1 over n is less than b. Okay, let's stop there just for a moment, because I would like to do this proof with two cases. Either at least one of a or b is rational will be the first case, and the second one will be neither a nor b is rational. All right, so case one. Suppose either a or b, maybe both, is rational. If a is rational, let me write, if a is a member of the set of rational numbers, then a is less than a plus 1 over n. Looking back at this, I'm going to bring this over. A plus 1 over n is less than b. Still just working off of this inequality. And then rational numbers are closed under addition. That's a direct proof to show. I didn't do it in the video because it's often a homework problem. So this would be rational. And so a plus 1 over n is a rational number between a and b. If b is rational, we actually already have it on the board. The one that we can take if b is rational is this one. So b is rational, 1 over n is rational, b minus 1 over n is a rational number between a and b. And that wraps up this first case. So if at least one of the endpoints is rational, it's not too hard using the Archimedean principle to construct two numbers, at least one of which must be rational by the hypotheses of this case. Case 2 will be that both a and b are irrational, which means that I can't do this. We are actually going to keep this inequality, though, and use it for case 2, so that's why I wrote it first before case 1. In a moment, I will erase this, and we will start here with case 2. So I'm going to erase all of case 1. Make sure you've written it down if you are still doing so. Then I will pick up case 2, given that we've already gotten this far. Now for case 2, we are going to assume that A and B are irrational, but I just worked back through the proof in my notes, and I realized that all I ever really need in this proof is that A is irrational. So if you'd like to, at the end, what you could do is take the work that we're doing in this video and turn it into a proof where the two cases are A is rational and A is irrational, because A is one of the two. And I think that will give it to you. So I may have been a little bit too precise with how I named these cases. Okay, let's assume that A is irrational. Notice, let me write it here, that just from this inequality, A times the number capital N is less than B capital N minus 1. Okay, so there's just some algebra. A times capital N is not an integer, because if it was, let's say it was some integer k, then I could write A is k over N, and that would be a rational number. So AN is not an integer. Since A is irrational, AN is not an integer. It's sitting between two consecutive integers. Let's call the integer to the right m and the integer to the left m minus 1. It has to be m minus 1. So choose m to be the, let me just write it as the ceiling function, just for shorthand. But I mean by this, the smallest integer larger than an. Then A times capital N is less than M, which implies that A is less than M over N, which is a rational number. So it would be great if I could show that this rational number was also less than B. We can do that by using this inequality. M minus 1 is less than AN, because again, M is like, here's AN, it's not an integer. So here's an integer, and here's 1 minus the integer. AN is sitting between two consecutive integers. The one on the left is m minus 1. It's less than AN, which is less than BN minus 1. So just comparing the left side and the right side and adding 1 to both of them, we get that m is less than B times n. Let me write that here. So therefore, B is greater than m over m. We conclude that A is less than m over n is less than B, and since m is an integer and n is a natural number, m over n is rational. All right, so that wraps up the second case. If you read back through this, I hope you agree with me that I actually never needed to know anything about B here. So what you could do is just case 1, A is rational, and build that A plus 1 over n number that we did. You don't need to use B if your two cases are A is rational and A is irrational. So you could actually rewrite the first proof just based on the rationality of A. By first proofs, I mean first case. Okay, so rational numbers are dense. There's a way to get from this a corollary, which is that irrational numbers are dense. I will readdress that question later. It's actually a very fast proof if you already have this, which we now have together. It's often a problem I give as a homework problem, so I might not do the full proof in a future video, but I will return to this idea that irrational numbers are also dense. So between any two numbers on the number line, as you zoom in, you always see more rationals, you always see more irrationals. I want to now use this result to prove a pretty well-known fact. Now I would like to use that result we just have about the density of rational numbers to show this well-known statement in mathematics, which is that if you have a number strictly between -1 and 1, so r could be here, if you raise that number to higher and higher powers, you move closer and closer to zero. So, if you have the number 1/2, squared is a fourth, cubed is an eighth, etc. So numbers between -1 and 1, when exponentiated, shrink to zero. We haven't defined the formal notion of a limit yet. So what I've done here is written this characterization in terms of a positive number epsilon. So what I'm saying is that given some number r, strictly between -1 and 1, and any arbitrarily small chosen value of epsilon that you like, so you can imagine taking an extremely small positive number, there is an exponent out there, which we will characterize as some n from the set of natural numbers, so that the size of r raised to that natural number n is smaller than epsilon. The idea with this epsilon statement is, we're trying to get very close to zero. If epsilon is, say, here, then I can find some natural number capital N so that the size of r to the n is perhaps here. It's less than epsilon. It's a positive number, so it's between 0 and this fixed value epsilon. Okay, but epsilon can be made arbitrarily small. So while this is a perfectly valid choice of epsilon, so is this one. And so then it's like, okay, for this much smaller value of epsilon, I might need to have a bigger exponent, capital N, but I can still find one. And then for this even smaller choice of epsilon right there, almost at 0 on my picture, I can still go find an exponent so that the size of r exponentiated to that value of n is between 0 and this teeny tiny value of epsilon. So that's this notion of arbitrarily small. You can always take epsilon and just keep moving it closer and closer to 0 and still find a term of this form between 0 and that value of epsilon. So for now, that is our notion of kind of moving closer and closer to 0. All right, there can be different ways to show this, but I thought it would be fun to use this idea of density of rational numbers. So in just a moment, I'm going to come back, and what we are going to do, just give you an illustration of what will happen, is repeating this picture. R could be negative, but let's just work with the absolute value of R and say that it's here. By density, I can place a rational number between the size of r and 1, strictly between them. And then this rational number is something I'm going to be able to shrink because I have a little trick to show you, but we'll basically squeeze r to the n between 0 and this rational number raised to the nth power, and we'll show that that can be made arbitrarily small. The first thing I'm going to do in this proof is introduce in that rational number I just highlighted a moment ago. Its existence is given to us by the density of rational numbers. So by the density of rational numbers, there exist an R and Q. I'm already using the letter R, never mind. Let me actually just go ahead and identify the numerator and denominator of this rational number. So there exists P and Q from the set of natural numbers so that the absolute value of R is less than P over Q is less than 1. P over Q, it's between a non-negative number and 1. So this is going to be a positive fraction. So I can take both of these integers to be positive. Q could never be 0. The denominator could never be 0. P is not 0 either because I can make it close to 1 if I want to. And it's going to be to the right of this non-negative number. Okay, so P is definitely not 0. That's why I said that they are both specifically chosen from the set of counting numbers, natural numbers. They're both integers. So let me say how P and Q have to relate to each other. Since P is less than Q, our fraction here is less than 1, that means that Q is at least P plus 1. Q is greater than or equal to P plus 1. So we're working with integers here. So this could be like 3 and 5. So I know that Q is at least 4 to make, okay. So the idea is integers are separated by 1 unit. All right. Now let's choose epsilon to be greater than 0. I want to pause here because this is a phrase that we write down all the time in real analysis. In a proof, as soon as you've written this expression, from this moment forwards, you think of epsilon as fixed. I'm not going to tell you what it is because it needs to be arbitrary for that demonstration I was doing where I was scooting forever closer to 0. So you don't give epsilon a value here when you're thinking of it as an arbitrarily small positive number, but from this moment forwards, whatever epsilon is, it is fixed in stone. It's an unspecified number which is fixed somewhere on the number line to the right of 0. By the Archimedean principle, choose, am I using capital N yet? I am not. Capital N in the set of natural numbers so that 1 over n is going to be small. And I'm going to go ahead and tell you how small it has to be. In this proof, I'm going to need it less than epsilon over this natural number p right here. It's mysterious at this moment why. So if you're like, where did this come from? You don't know yet because you haven't seen the work. So when you read real analysis proofs, if you're reading through a book or something, anytime you have an inequality where you're like, how do they know to do that? It means that somebody, the author perhaps, worked out some algebra on scrap paper and then realized what had to happen. So this kind of thing is often the last step that you determine when you work out a proof for the first time. Well, I've already done this proof, so I know that this is the inequality that we are going to need, but you'll see in the rest of the proof where I must have come to that conclusion. Okay, here's the part that I think is fun. So I'm going to use Bernoulli's inequality. Bernoulli's inequality, I'll write it down in generality right here, is a proof by induction that I actually did in the logic and proof writing series. It's just straightforward induction. It doesn't need this result at all, so it's safe to use it. And you can go visit the logic and proof writing series that I have on YouTube if you'd like to see this proved. The statement is that 1 plus x to the n is greater than or equal to 1 plus nx for any number x greater than or equal to -1 and index or exponent in here from the set of natural numbers. Okay, so this is Bernoulli's inequality expressed in general. Here's how I'm going to use it. I'm actually going to take the reciprocal of our natural number. We have p over q. I'm going to flip it and exponentiate that. So q over p raised to the, not just general, and I think actually what we can do right now is go ahead and raise this to the specific natural number that we have already identified. Well, q is greater than or equal to p plus 1. So actually, let me go down in size and replace this numerator with p plus 1 over p. And now let's take this numerator and split this up into 1 plus 1 over p to the n. Now this looks exactly like this. So we can say, thanks to Bernoulli's inequality, maybe I'll mention that's coming in right here, that this expression is greater than or equal to 1 plus capital N times this quantity. So here x is the 1 over p. So we have 1 plus n over p. And then just knock off the 1. So this is greater than or equal to n over p. Okay, so that is something about q over p raised to the n, but now let's go the other direction. Consequently, going back to what I'm actually interested in, it's the size of this number r raised to the capital N power, where n is what I've chosen. So this is like an existence about capital N here. I've chosen the n that we are interested in. So the size of r raised to this capital N is less than or equal to p over q raised to the capital N, which is going to be less than or equal to the flip of this, p over n. So here I need to take reciprocals and reverse the inequality. So this is greater than that, which means this, flip it, it's less than or equal to the flip of that. I think I may have said that wrong, but p over n is greater than or equal to p to the n over q to the n, and that's what we wrote here. Sorry, I think I flipped something incorrect in my inequalities right there, but this is true. But 1 over n was chosen via the Archimedean principle to be less than our number epsilon, whatever it was, divided by this fixed number p. So p is just a fixed number. So this is less than epsilon over p times p, where here I've taken this 1 over n and replaced it with epsilon over p and gone up in size, the p's cancel and we get epsilon, and that's exactly what we wanted to see. So again, this tells us that no matter how small epsilon is, it could be like 1/1 billionth. If you take your number r between -1 and 1, take its size by computing its absolute value, there's some power of that size of r, which will be between 0 and 1/1 billionth or 1/1 trillionth. You can get closer and closer to 0. So again, we don't have the formal definition of a limit yet, but our idea with this statement is that r to the n, when r is between -1 and 1, that just is going to shrink to 0 as you keep exponentiating to higher and higher powers. Okay, I just wanted to do this exercise. I just think it's really nice to bring in this rational number kind of sitting between the size of r and 1. I always love anytime I can use Bernoulli's inequality. So this is just kind of an exercise. And again, if you'd like to see the proof of this by induction, you're welcome to go check that out now in the Logic and Proof Writing series. Thank you for your attention.